it working?
Seems to have connected.
Yep. Yeah, it's working. Whew. So we're here to discuss the Lisp, and previously we had code examples. We have tried to run ACL2 theorem prover, did some example proofs, and I have discussed about some theoretical problems about the CPU verification and some RTL design problems. Here we can see a recursion for the factorial function, which is defined as follows. In the beginning it's the fun, this is the name of the function, this is the argument. Then we have an if then else expression, and in the else part we have a return of the recursion for n-1 step. So everything in Lisp is a list. So as you can see, we have an operator in the beginning with the two arguments. It's 5 and 3, which is the result, this is the result of this expression. It equals to 8. This is a subtraction, multiplication, and division. So also we can create a list inside the Lisp. Here we can check the name of the list. Here it's the beginning of the list, and we have to put here a concrete values 1, 2, 3, 4, 5, and then we can use this list inside some functions. For example, function first. This is the basic built-in function in common Lisp, which is called the first. We can have a rest or the list. It's, for example, it's the head, which is we're calling the head, and the rest. We can do the following operation, adding an element to the beginning. For example, cons 0 to numbers. We can find the length, and also we can define a square function to get the power of 2 for any argument. For example, square of 6 is obviously 36. In Lisp we can't define an infinite sets, so we have some trick for these things. For example, this function is checking the odd or even numbers. So we have predefined function which is even p. If it's true, it's return even. If not, it goes to odd. Okay, so we can define functions applied twice, which is the function applied to the function. For example, we can put the function as an argument. For example, apple twice goes here. I recommend you to follow this link on the GitHub to check another examples. Last time we tried to solve some kind of problems from this list, which is called 99 Lisp problems, which is quite popular for Haskell, for another functional programming. As you can see, we have tried to solve some binary trees, graph problems, and other popular problems like 8 queens problems, solve for Sudoku, and many other interesting tasks. Okay, so we can start from the what's the problem of the verification. For example, we have the following flow chart for the program. It has 3 states, A, B, and C. In this flow chart we have a precondition n above 1, and we have a loop invariant for this type of expressions. So it means that for every I, for every possible state, this expression is true. And we have the postcondition for the state C, which is the following: n plus 1 multiplied by n divided by 2. This is the result of our program. So we have to, the main problem of the verification is to define the algorithm. How can we formally prove logically using the mathematics and axioms the following statement? If this is true, then it follows the invariant. If the invariant is true for every step, then it follows the post condition. So for every possible input, we have the predicted output. Previously, we discussed a hardware verification problem for CPUs. As you can see, it's a brief overview of the main CPU blocks like control unit, ALU, registers, memory management unit, some keyboards, inputs and outputs, and the bus. What is the chip? It's we define this like an abstract finite automator, and said that it is equivalent to some kind of tables, some kind of the structural representation of automator, which is the following. It's the function of the changing the states and the output function. For every input, for every time state, we have the following rules. So here is the lag operator. So for the next tick, we have the following changing the state, and for using this type of abstractions, we can define every possible hardware design. So we can have circuits, following expressions, tables, and we discussed the data flows. For example, we decided what's the input for every wire here, for C, T, etc., and what's the output. So as you can see, it's the clock wire, it's the some kind of the input, it's the some kind of data flow or the states, and the output Z1 and Z0. Here, this is the equivalence between this representation and this. So, for example, if we in the state 1, 1, if the input x equals to 1, the output is equal to 0, 0, and we go to the state 0, 0. If in this state, the input can be equal to 9, and the output will be 0, 9, and we go to the next state. So it's mathematically proven that using this representation, we can use this kind of assignments, tables, and finite automator, and it should be equivalent, and we can minimize and decide about those designs. This is the example of the arithmetic logic unit. This is the core of every CPU. This is the real schematics of the combinatorial logic circuit from the CPU. It's called 7181 for 4-bit ALU addition. So we can represent those blocks as a multiplexer, carry in and current to find the 1 bit. We can select a function and or, and we can find the result from the A and B. Previously discussed was the Quine method, but it's some kind of the formulas. We decided that it's just an abstraction, and for example, in the real instruments, in the real IT environment, we can just use some Verilog coding, and it will be out of the scope. It will be implemented inside the under the hood of our software. So previously I recommended to check the VL Verilog toolkit and the x86 ISM module inside the ACL2 for hardware verification. There are other frameworks to use it, and then in the beginning we can check the following example. This is the website gdigital.js. Here we can find the full ladder example. So this is a system verilog file, which is automatically generated from this library. So in the beginning of the model we have some inputs and outputs. It's a wire. Each statement is a wire, and for each wire we have an operation. This type of operation and this type of operation. This is the definition of the half adder, and now we are able to get some kind of the full adder. Let's check what's the circuit of this code. So as you can see, we just define the expression for this kind of functions and put those models inside this circuit, and the output is our variables O and C. This is how it works. Now our main task: how can we design those kinds of programs without any errors? How can we define that it is some kind of invariant is true for every possible state? For example, I recommend you to check this video. This is a formal hardware verification with plenty of examples. How can we use ACL2 for real hardware, analog and mixed verification? The main, one of the examples from this video is the following. So we have an RTL code, we have a design expectation, and we have a real netlist. We have to find the answer for the following question. Is the clock 1 and clock 2 are the same? So the answer is no. So we can find some kind of the software, some kind of verification to formally prove the statement. So let's check the definition of the Verilog. Here we can see a bus decoder which can be generated into the following circuit. Okay, just new file, create file. Yeah. So this is a bus decoder for which has the input wires clock, the reset, and the following wires. So we do, as you can see, we don't need to communicate with each wire manually. Using those kinds of expression, we can have a result in the following picture. So this is the output. Let's check more interesting example. We have some kind of mux block inside some hardware. We have some clock input wire, reset, some additional wires, and we have some operational additional wires to do some manipulations with our codes. The another operator is the following expression. Just imagine that we somewhere predefined the bus decoder before this, and we are trying to connect our environment in the current state with the previous inner device. this is the following commands. We have to connect clock with clock wire, reset with the reset. We are able to connect wires as a decoders, and after this we can assign the output for this chip. So the end result of this kind of expression will be the following.
Sorry.
Okay.
No, I'm using my phone to open it. Sorry? No, I think sorry.
Okay. The another example is the FIFO. It's 8-bit hardware for some kind of the FIFO data structure. From the left hand side, it's the array of 4-bit register with size of 8. For example, here. So in this we have output data and the 8-bit array. And the size of this array equals to 1, obviously. From the left is the width of the wire, and from the right we have dimension of an array. We can define an additional parameters such as size of the FIFO, number of bits for addressing, and additionally for this kind of example we have registers, which is quite more interesting because we have the following expression always. For registers we don't need to predefine those kinds of expression like an assign. We have to define FIFO operation using register with the following condition. If the clock or a reset is true, then we begin. So in the Verilog we have two types of assignments, blocking and non-blocking assignment. This is the non-blocking assignment, and if we have for every register we have to initialize this register with the zeros or some value. If it's not defined here, this is not a register, it's something else. And using this kind of assignment, it will be it will be applied just immediately. And using this kind of non-blocking assignment, it will be run on the next time frame. So here we can define the logic of our chip and hardware. If we didn't press the reset wire, we are able to define the following expression. For example, we have data in, and for array of with this expression we have the following statements. So as you can see, it's like a C coding. In the Verilog we don't need to write every possible state, connect each wire. It will be automatically generated using those expressions. Okay, so what can we do inside the ACL2? We have to define the specification. What should we do with the data block? What should we do with some kind of the hardware? We can model a CPU blocks in ACL2. I will show you how to use the library which is called the CV and VL to model CPU blocks and other hardware using some expressions. We have to write some properties and assertion, and we are able to test automatically and find the performance and verify that everything is okay. And ACL2 is able to document and write some review inside the files, which is called xdoc format. We are out of the scope to check all of those CPU blocks inside the ACL2, but we will discuss this example, 16-bit LEU inside the ACL2 verification, and other kind of CPU blocks will be discussed in the future. I recommend also to solve those kinds of problems, and I will upload a solution for those problems on my GitHub on the following link, ACL2 problems. For example, the first problem is about how can we create a bus decoder plus FIFO model inside the one device. At first we have to write a Verilog code using some kind of the model.v file, and then we will have to define the properties, outputs of this hardware, and implement this inside the ACL2. Average calculation model calculates the arithmetic mean of the last 2 in the power of k submitted numbers. So as you can see, we are able to calculate some expressions using the representation of the structural automator. So it is quite useful for fast manipulation with the numbers in the application like high frequency trading. It's like with data manipulation and machine learning application, because using this knowledge you are able to implement it very fast. I also recommend you to focus on the encryption modulation. We are able to create in the Verilog some block ciphers, for example, blowfish representation, so those schematics. And also we are able to verify those circuits inside the ACL2. I would like to verify the universal register interface and generate a gray code sequence. Another problem is just a cyclic stage from left to right. It's quite common, for example, in the C language. And so we are able to implement some kind of the hardware which is doing the following: division by a constant c, it's like a modulus parameter. We are able to count the number of individual bits in the input vector, return the result as a double number. And the last problems are the following: it's an addition of two numbers with saturation. If this problem is difficult for you, you can just return the max value of these two numbers. We can calculate the most significant bit of a double number. Then number can also be issued as a double number. So let's check the following. So as you can see on the slide, we have some kind of the history of this ACL2 theorem prover. This is the Edinburgh pure Lisp theorem prover. Then was a computational logic, some kind of the NQ theorem prover, and the topic of our discussion is ACL2. So there are a lot of theorem provers to verify this kind of hardware, and we have IEEE 754 floating point standard for elementary operations, which are precisely defined inside the ACL2. And also it's an interesting example. For example, fdiff operation. In the beginning we have some lookup of the table, we have the register D, we have some multiplication, comparison, and other stuff. For example, how can we define the formal model of those kinds of codes for hardware? For example, we have a fdiff operation. It's the mode, it's the first argument, and the lookup register. For each step, we define the let expression. For example, for each variable, we have the following calculation, etc. And then we will get some results. And if we have this function, it should be total for every possible state. In ACL2, it is using the guard statement to verify the domain of the functions for every input. Now we are able to define a theory and to decide how can we prove this statement. As you can see, it's a common Lisp subset with defined events. Events, it's the some kind of expressions that define more actions for this kind of logic. In ACL2 we have first order logic, and it's the definition of the for example, we have implies, which is the imply statement, which has the two arguments. The first argument is the predecessor, and the second argument is the conclusion. And expression, it's just an AND operator for logic in the first order. We have some kind of inputs. For it's the number expression and the second number expression. For we are trying to say the following. So for two numbers, P and D, this is we are able to say that D is not equal to 0, and we have some kind of mode. And if it's true, then we have the following statement. With this kind of arguments, the fdiff operation equals to the following expression. This is our post condition. To prove this kind of theorems, sometimes we have to use, for example, 1200 lemmas. So writing proof inside the theorem provers is quite tedious. ACL2, it's a computational logic for applicative common Lisp. It's mathematical logic inside the theorem prover. It's untyped and it's strict, not lazy, and it is first order. So it's the main condition for this. For example, main practical condition for this, for example, we can define infinite sets and operate with the infinite sets. We have to define some kind of the predicate to emulate this kind of behavior. All ACL2 functions are total, always terminate on all arguments. It's quantify free, which means we have to use some kind of columnization, and this is the standard interaction between this theorem prover. So as a user, we define some kind of the functions, we define some theorem, then we have some libraries which are called books, and the theorem prover is trying every time to prove this automatically without any interaction with the user. We're able to define some kind of arithmetic vectors to use inside the ACL2. Also, have the following syntax. Okay, for example, we are able to use some kind of this expression inside the ACL2, like it's just in common Lisp. ACL2 supports 5 disjoint data types like numbers, characters, strings, symbols, and pairs. So we have the following semantics, and the beginning of the every theorem prover is axiom. So, for example, those kinds of expressions are quite obvious, and they are using automatically for the core of logic. This is the definition inside the ACL2. We can able to add a new axioms. And this is the derivation rules. And there is a measure of the well-founded ordering, such as for every recursive call for every function in a body, it can be proved that the measure decreases according to the ordering. The last condition means that ACL2 can admit only provably terminating recursive definitions. For example, we are able to define the following statement: append for the lists. Let's define like as a function app. Let's check this inside the theorem prover. Just check quit. Yep. ACL2. Inside the ACL2, we are going to define the following function. Okay, we have the append function for the lists. Now we are able to check the following statement. As you can see, we have the symbol T, which means true.
Does it prevent you from doing circular references, like if the cutter of the list pointed back to the list itself with that?
As you can see, we just tried to put inside this expression just concrete values. And it's just using the append function or just app.
Okay. So you can't
and we will get the calculation of this function, or this kind of function, and the end result will be the same as following.
So you can't have self-referential lists?
Yes.
Okay.
So in those kinds of situations, we can define some variables using def theorem function. So, for example, we are able to prove the following statement. So it's completed. Sometimes it's not usually goes well, so we have to define some goal, proof goal, and use some kind of expressions to prove until the end. But in this kind of situation, we proved it's very fast. Okay, we define the function app, and we are able to find the proof for this statement. So for every possible A, B, and C, it is equal to append at first A and append the first B and C. Yep, it's proved. So this is the example of the induction. Sometimes we are not able to prove it into one step, and we have to use the following statement, for example, and P, which is calling the induction inside the theorem prover, and we have another sub-goal. In this inside sub-goal, we use another kind of function to get the result. So So what's going on inside this theorem prover? We are putting some kind of formula. Then the theorem prover is trying to use some simplification, which is just rewriting tactics. Then we have a destruction elimination. It's like the logical elimination of some kind of unnecessary statements inside the logic. We have some kinds of equality, generalization, elimination, and in the end we are trying to use the induction. Besides this, we find the evaluation tactics, propositional calculus. We are able to try to use some binary decision trees, which are crucial for some kinds of hardware designs. We are able to use some set solvers and rewrite rules. But mainly, if the SAT solvers and BDD tactics are not able to prevent from the failure, we have to use some kind of deconstruction tools. Some more realistic examples: a simple stack machine, a simple expression language model, a simple compiler, prove that the compiler is correct. We will formalize a machine with the following expression. So imagine the function m with following arguments: programs, environments, stacks, and the return of this function is stacks. For example, a simple program: load a, push 3, and multiply. We have the sample environment, for example, those kinds of values: 20, 30, minus 5. And then we have some stack, for example, for the push operation. And the end result is the list of states. So here we have some criticism. It's trivial. There is no store instruction, no program counter, no break, no interactions, no iterations or loops. So we are able to understand how can we involve in some kind of the logic of the program. Another interesting example: how can we implement some semantics inside the GVM? Our M6 model is based on an implementation of the Java 2Me implementation, and some representation of the Java inside the theorem prover. For example, we are able to deep embed the language of Java inside some kind of the Java low-level machine. Put into the Lisp file using this kind of expression, get the theorems and try to prove them. We have the same technique for the Verilog for the hardware verification. So, as you can see, we have some kind of manuals. This is the official website of the ACL2, and let's click to the tutorials. Let's go to the hardware verification. So the most foundational framework for hardware verification in ACL2 is GL, which is the symbolic execution for the hardware. It's able to represent some kind of proofs, debugging. As you can see on the basic tutorial, what should we do with the proof? For example, we have the following statement, and we're able to define those kind of expressions and to define the theorem and some kind of logic. But for real applications, we have some Verilog representation and the SV system Verilog. So let's check the following tutorial. how can we verify a simple 60-bit combination of arithmetic logic unit model. In the beginning, we have to implement the following statement in package, which is called the SE package. And for the preliminary setup, for example, if we have 2 dots, we have to start our ACL environment in the necessary directory to get those kinds of files. So because of the lack of time and computing power, we are not able to test every possible line in this file, and I will just discuss what's going on inside this file. This is a real example of the LEU verification design. So the common idea for those kinds of tasks, we are trying to implement some kind of the arithmetic logic unit. For example, translating. Yep. Here we can check what's going on inside our LEU. So this is the Verilog file. We define some kind of operators, output and input wires. It's an array of wires. We have some default clock, and we define some kind of logic here. So this is the definition of our hardware. Now we are going to upload those libraries from the Centaur books for the ACL2. Then we are going to make some events, some definitions. This statement is the reading of the VL design or this file. So we're just trying to read this file inside this ACL2. Then we are able to simulate this environment to get the data frames, or for example, how can we implement the hardware and how the clocks is working. For example, have a tool which is calling GTK wave. To implement some kind of testing. So this is a toolkit for getting the signal from the hardware and visualize in the most appropriate way for our hardware. Using those statements, we are able to save some logs of this hardware, which are defined inside the Verilog, and get this file as a TXT file and visualize using this instrument. Then we have to define some theorems. Let's check. We save some opcodes for this verification. For example, what's going on inside there? As you can see, we have some predefined function def save event. We have the framework GL, which is symbolic execution for the Verilog, and we have some kind of hypothesis. So this is a logical expression. And then we have to, if this true, we have to prove the following statement. So as you can see, we have done this means that if we have some kind of plus operator inside the Verilog, it is the same as a plus operator inside the ACL2. And then we have the following statement. If our LU test vector is correct for every possible value, then we have the following output. Is the addition of the A and B wires, and the output is 16-bit long. So this is our theorem. Then we do some G-binding, which is doing some auto-binds with the libraries inside the GL framework, which helps to ACL2s to solve this theorem. This is the example of some kind of deconstruction rules. We have some auto-bindings, some kind of tactics, and we are able to define more complex theorems. We are using local statement to define some kind of environment. For example, in some kind of situations, we are able to simulate following statement. With the following conditions, we have some outputs. In the next example, we are able to use some kind of set and BDD expressions. For example, here tutorial testing. Yep. So the optimizing BDD order using some kind of bindings. We are trying to improve this using this statement, which is the mix or the some kind of natural. So we say to the ACL2 that we have the some kind of operator. We have that A is a 16-bit input wire, and B also is 16-bit input wire. Then we're trying to decompose this statement until it goes to true. The same logic for the SAT solver. We're trying to use some kind of a SAT technique to or some kind of the brute force of this logical formula. Okay, another interesting example is the X86 ISA verification. So it's quite useful to construct a compiler, verified compiler, which are verified inside for particular CPU instruction set. As you can see, we are able to open the tutorials, for example, Intel software development manuals, to check what kind of commands and some kind of assembler language are implemented for this kind of the hardware, and try to verify the statements that for example, for every possible execution we have the conditions. For example, if we want to verify some code using some GCC low-level LLVM compilers, we have to verify that there is no missing opcodes, the binary code is true. For this kind of task, we have to find the ISA model inside the ACL2 to define those statements. You can find those statements inside the source code inside the books. For example, for LU, for system Verilog, for another kind of simulations, we are able to find some examples and just try to use in the real environment. For example, like in this repo. Okay, so what next? We have two types of the VL libraries inside the ACL2. It's old edition VL Verilog toolkit, and the modern one is which is under the development. It is the same like as we discussed for the SV library, but with more flexibility. For the RTL design, we are able to verify some modeling algorithm. It's for floating point arithmetic, for modeling algorithm in C++ and ACL, but mostly it's for programming rather than just real hardware design. So for register transfer logic, we are able to simulate, for example, modulus operation with those kinds of expressions. So as you can see, there is no deep embedding or the Verilog language inside the theorem prover. We are just trying to decide about the logic of the algorithm. We are trying to model using some kind of functions. Another interesting example is bit vectors. Concatenation, for example. So this is examples of theorems and definitions. Yeah. Another topics are the eSym, which is symbolic execution, which is simple hierarchical bit-level cycle-based register transfer level hardware description language. It is not quite popular, but I recommend to start to solve those problems from those slides and check the solutions on my GitHub. And then using this kind of books like a CV inside the ACL to try to verify and write some proofs for the ACL2. The practice is very important in this field. We have some successors of the foundational libraries like a GL, which is quite similar to the previous one, and mostly it's just like a syntax sugar. It's more additional instrument. It's some kind of additional instruments to prove expressions, find counterexamples, do some simulation, testing, and get waveforms of our logics. So that's it.
Thank you. Great presentation.
Thank you. So any questions?
So the Verilog module, so it is parsing Verilog files for
Yes.
correction.
as you can see, you can check how it's going. Goes to the hardware verification, SV book. Inside the SV tutorial, there is some kind of the description. We are trying to translate Verilog inside SV expression design.
SVEX is the internal representation.
Yes.
Can we just not use Verilog but work directly in SVEX, for example?
Possibly yes, because we have some kind of additional functions. You can find this inside the SV description. For example, expressions, yes. Because it's a common Lisp syntax, you can directly manipulate with those values.
So I was thinking if it's maybe possible to build a whole EDA toolkit around it rather than just using it for formal verification.
Yes, I also recommend to, if we're trying to use some Verilog, we are able to use some real program with Vivado IDE on the real FPGAs, on the real hardware. And after this, we can just test. And for this kind of Verilog, we can try to generate a symbolic vector expression inside the ACL2 and try to verify some statements about this hardware.
Is there any VHDL support for ACL2?
I haven't found this yet, but as you can see, mostly those packages and libraries are represented inside each particular version of ACL2. So mostly it's for Verilog and system Verilog expressions. And if you would like to some VHDL verification, you are able to some modeling inside the ACL using eSIM and RTL design. But it's like model checking inside the T-layer class for distributed systems rather than just working with the real code. There is no embedding.
What is eSIM? Is it like Verilog or what is it? Is it like SVEX? So it's another internal representation? Or?
Yes, it's another internal representation, but not a concrete syntax. It's just another kind of language inside, particularly for modeling the hardware.
I see.
For example, let's check the eSIM expression. What's inside this? Okay, this is how we can include book.
You can zoom it in with control.
Yeah. Yep. This is how we can connect our books with expressions. So we are trying to define some expression inside the eSIM. Here. So UART it's some kind of definition about the domain or the function. With those kind of expression, we are trying to verify that everything is okay for this kind of expression. So it's not quite clear to find the visualization of this kind of expressions, but I recommend you to find papers with definitions and the real coding examples.
I might have missed this at the start, but is ACL2 a library built on other common Lisp implementations, or is it its own common Lisp implementation?
ACL2 is written on the ACL2,
Okay.
so it's a subset of the common Lisp. So if you would like to install ACL2, you have to, for example, compile it from the sources using some kind of, for example, common Lisp compilers like CBSL.
So it's bootstrapped for many common Lisp implementations.
Yes. It's quite old. It's the beginning, like in the end of the 80s. So nowadays we're able to have some kind of the IDEs, visual programming tools. We have some kind of the modern approach like a Haskell language or AGDA.
ACL2 is most common, I guess, for industrial use.
Yes, it's as you can see, we can check, for example, another examples for the RISC-V verification. It's the SAIL project for inside the Isabelle theory improver. It's using the Z3 SMT. It can be using for Hall 4 and Cork, but this is the infrastructure for verifying some kind of the hardware for the open source RISC-V and some kind of the ARM-A. But there is some kind of the implementation of the x86 using the ACL2 instructions. So for the real applications for the modern approach, I think it's more appropriate to use SAIL. But in some industries, if the legacy is important, you have to use this kind of software ACL2. And also ACL2 is applicable for some kind of combination with the analog devices and the digital devices. For example, if we have some control of the digital device using some digital hardware, and this digital hardware is controlling some kind of analog circuit, we have some kind of a physical invariant for this kind of hardware, and we can formally verify this behavior inside the ACL2.
So yeah, we are probing the analog device and comparing the result of the probe with.
Yeah. So ACL2 is able to use some kind of simulations and generate some kind of outputs for your Verilog code.
So I haven't done formal methods before, but on the lowest level, is it converting everything to stat expressions or like equations, and then
so the main idea of the verification is the following. For example, imagine this flowchart. So it's the simplest program with the following statements: states A, B, and C. We have to prove the following logical expression. If this is true, then it should lead to the invariant, which is true for every possible state inside the loop. In the end of the loop, it should be the following. It led to the following expression. If every statement from the precondition to the postcondition is true, then we verify the program. This is how we are able to cover infinitely many possible states for the program. For another approach, for example, model checking, we have some kind of the simulation for some kind of this expression, for example, invariance, and we are trying to dynamically execute this model to check this kind of statement and verify this is true for many values, for example, for millions of states. But using some analytical approach like theory improving, like ACL2, you are definitely able to verify infinitely many states, programs, and hardware.
So it saves a lot of time compared to a more direct approach of checking.
Okay, if you're just trying to test your hardware, you can just check small amount or small subset of all possible inputs and get some outputs. If you are trying to some modeling with a theory improver, you are trying to simulate infinitely many states by design. So another interesting examples. Okay, so I recommend you to start coding in the Verilog those problems, and after you get these .v files for each problem, you are able to embed this inside the ACL2 using the SV book and try to verify the try to define the precondition and the postcondition for each case. For example, what's the the postcondition for the bus decoder? Just okay, we have some kind of inputs, and these kind of inputs are generated in some kind of value, which is assigned inside, for example, these kind of expressions. So this is quite obvious to get a postcondition for the ACL2 from here for the bus decoder. But for example, FIFO implementation, it's not so easy to find the invariant, but it's okay to just try to write some kind of expressions using this representation. I also recommend just to use, just to think about how can we implement, for example, encryption modulation using hardware in Verilog. It's a very interesting task, and which is very applicable, for example, for telecommunications, for signal processing, etc. And UART Driver and I2C Driver. It also is an interesting task because we can able to just to convert from the USB to another devices, like to simulate the behavior with the microcontrollers in another embedded systems. So I think that's all. If you have any questions, just go to the Telegram channel and chat and ask questions.
Yeah, and we also have the Meetup group as well.
Yes.
With the discussion board.
Okay.
Thank you.
Thank you for your time.